Good morning. Let's see. Get things going here. As I'll say every class, please feel free to turn on your video and unmute yourself if you want to say things. Happy to see faces if you want your face to be seen. But again, I get if you don't want to turn your video. But my video is on, as it will always be. Let me change my view here. I'm going to pin my video so that my board is easy for everyone to see. Couple things before we get going today. Let's see. I feel like there was a couple things. First off, I know I emailed a bunch of you just like 30 minutes ago that you hadn't submitted your quiz yet. And then after that, I realized that I had accidentally made the quiz due date for today instead of yesterday. So if you got an email from me about not having your quiz done yet because you were planning on submitting it today, go ahead and still submit it today. I apologize if I caused any confusion. Generally, quizzes will be due by the end of Monday, and if they end up being late, that's fine. I really just want you guys to do them. So again, please, if you're gonna submit your quiz today, go ahead and do so. I apologize for the confusing email and due date stuff. But next week, the plan is for the quiz to be due on Monday. The plan is also that I will, what's the thing I was gonna say? I will probably post the quiz a little earlier than Monday morning. I might even post it on Friday so that you can do it over the weekend if you want to. You shouldn't spend a ton of time on it. It's not meant to be like super hard or lengthy. I'm just trying to get an idea of where you're at. And then my plan is to try and get them graded as soon as possible so that you can have some feedback on them. So let me move some things around here. Excuse me. I feel like there was something else I wanted to go over about Canvas, but I'm not sure. I will also get your grades updated for the things you submitted once they're all in there sometime this week. Yeah, sorry, my brain. I feel like there's something else I meant to be saying to you guys, but it is not coming to me at the moment, which is fine. What else? There was another thing. Oh, I know what it was. Where did you go? As far as, I don't remember if I don't think we did this last week. So I've changed the way I'm taking attendance. So hopefully you didn't have to log in today. You said to enter a password, or hopefully you didn't have to do too much to log into the Zoom class. I changed the settings so that you shouldn't have to keep logging in every time. You should have to enter a password though. Did you guys have to, so if you could give me a yes or a no, did you guys have to enter a password? No. Okay, you didn't have to enter the Newton password. Interesting. All right. What's that?
I did.
Oh, okay. All right. I wonder why some of you did and some of you didn't. That's interesting. I mean, it's not that big a deal, but just curious. What else here? Oh yeah, so I was talking about attendance. Sorry, where'd my attendance thing go? So if everybody could quickly, I mean, sometime during class today, if everyone could go to the link that I just added in the chat there and enter your student ID number so that'll track your attendance for me and it'll make it easy. So if everyone can go fill that out when they have a minute, I would greatly appreciate it. All right, I think that is all the business. Actually, so one more thing. I just also wanted to remind everybody that starting tomorrow, there will be online drop-in tutoring. So you can schedule an appointment with a student tutor. And the link to that, if you want it, is, sorry, one sec. One moment, please. If you're interested in getting some help from a student tutor, feel free to go to here. And you can click on the link to make an appointment. And that'll be available starting tomorrow. And you can make, I think, a half-hour appointment with a tutor in any of the math classes that are the usual classes we help with, which I think is a good resource to use because, well, all the specialists are not available as much as we usually would be. So the student tutors will kind of be filling that role this quarter. All right, as far as material. So I wasn't able to watch Merckx's lecture yesterday because I feel like he posted it kind of late. So do you guys have any questions or things you want to see covered? I've got a couple ideas, but if there's anything specifically you want to see, now is your opportunity to speak up and tell me. All right, I'm seeing a couple things. You guys are also welcome to use your words. You can talk. It's okay.
Just a question. Is there a reason why? Okay, because I don't mean this to sound totally rude, but Sam is really bad at teaching. And a lot of the students in general are just really, really behind. Like I see that someone like put like antiderivatives, and we're like still talking about, we're barely like scratched the surface on implicit differentiation with like the is there a reason? Because I feel like there's a lot of people in FAMs, like I don't know if anyone else sees this, but like is there a way that you could join like one of FAM's lectures just to see like where we're at in lecture?
What time is his lecture at?
1:10 to 2.
I can't. I teach a class at that time on Monday, Wednesday, Friday.
Okay, yeah, no worries, because it's like
you're kind of cutting in and out.
We got really behind. He doesn't post like, he's just really bad at teaching, and so it's kind of hard to like know what we want to learn because I actually don't even know what we're learning right now.
Sure.
Yeah.
So unfortunately, there are differences in people's teaching styles and abilities. And I see everyone talking to stuff. So I would say this class we might be ahead of where FAM is at to try and kind of keep you guys up to date with the material. I can definitely, and I saw someone said he posts his lectures on Canvas. I'll definitely go try and watch them. Also, one thing to know just as far as watching lectures is I'm watching a lot of the lectures at 1.5 or double speed just to kind of get through them more quickly. Also because I know the material well, so I'm just trying to hear what they're saying. But if you find the professor is teaching something really slowly, you can also watch it at 1.5 speed and kind of try and see it. And then if there is something you need to actually hear, you can pause it or whatever. So just so you know, that's an option. I've definitely been using it. But yeah, unfortunately, there are differences in people's teaching ability and the pace at which they cover the material. So that's something that hopefully this co-class will help kind of compensate for. We'll try and help you understand the material, but I'll have to kind of go look at what he's doing to kind of help you guys better know what you should need to know. So I see lots of things you guys are saying. So let's see. So we want to talk about implicit differentiation and exponential growth, decay and growth problems, antiderivatives as well. I think we'll do antiderivatives more towards the end of class today, and we can definitely do some guided practice. In fact, let me see it. Let me go look. I know I've got a handout somewhere that I wanted to get to you guys. So 1 second. I thought I had it on my computer, but I did not. So let me look in the box real quick here. Whoops, that's not where I wanted to go. Sorry. We'll get started in just a sec with, I think it makes sense to start with probably implicit. Yeah. Come on, give me my stuff. Let's see, is it in here? No, I don't see the thing I want. Oh well. I know what I'm looking for essentially. So, okay. All right. So let's start with, so when you say implicit, well, there's kind of two different things I'm thinking of here, but we'll start with kind of the general idea, and then we'll go with where I think we want to be. Yeah, we want that later on. All right. And again, feel free to chime in if you have questions, concerns, comments. All right, so implicit. way to do that. Okay. So the idea with implicit differentiation is that you are using the fact or the idea that y is meant to be a function of x, even though we can't explicitly write it that way. It's implied that y is a function of x, which is why it's called implicit differentiation, but we can't actually solve for y explicitly. So an example, and I think we did, and remind me because I don't always remember everything very well. We did implicit differentiation in 16a, right? Like that was something that was covered in 16a. Yeah. So let's do an example from 16a to kind of remind us what we're doing. So let's say we had something like, I don't know, here's our equation. X cubed times y squared plus sine of x plus y equals x to the fourth plus y to the fifth. And our job here is to find y prime. A lot of this question is really more algebra than using calculus, but we still have to do calculus the first part. So the first step is to differentiate both sides of this equation. So I'm going to differentiate this. I'm going to have to use the product rule. So the derivative of x cubed is 3x squared times the not derivative of y squared is y squared. Plus, then the x cubed gets left alone. And the derivative of y squared is where we actually have to use the implicit part. So remember, we're thinking of y as some function of x. I'm sorry, I thought someone was talking to my wife in the other room. I was like, someone say something. So I'm thinking of y squared as f of x squared. And when I differentiate y squared, I'm going to get the derivative of some stuff squared is 2 times my stuff times the derivative of my stuff. Or I could write it as 2 times my stuff times the derivative of my stuff. So that's why when I differentiate something with a y, I have to end up having to multiply by y prime. So the derivative of y squared is going to be 2y y prime. The derivative, oh, sorry, not equals yet. The derivative of sine of some stuff is cosine of this stuff times the derivative of the stuff. What's the derivative of x? All right, say something.
1 plus y prime.
Perfect. And then on the other side, the derivative of x to the fourth is 4x cubed. The derivative of y to the fifth is 5y to the fourth times y prime. All right, I'm going to have to go close my wife's door real quick. We'll be right back. It's okay. I keep thinking students are talking. It's okay. All right, so that's the only calculus step in this problem. The rest of it is just doing the algebra to isolate y prime. So before we can actually do that, we have to distribute this term. We have to take this cosine of x plus y and multiply it to each of those. So I'm going to have 3x squared y squared plus, I'm going to write this with a 2 in front because that's kind of more normal. 2x cubed y times y prime plus cosine of x plus y times 1 plus cosine of x plus y times y prime equal to 4x cubed plus 5y to the fourth y prime. And then we're going to group all the terms that have a y prime on the same side. This is where we're going to have, so I'm going to bring them all to the left. So I'm going to have 2x cubed y prime plus cosine of x plus y times y prime minus 5y to the fourth times y prime equal to 4x cubed minus this term, cosine of x plus y. The rest of the algebra is to factor out the y prime here. So I've got a y prime. In fact, so this is where no, fine, I'll do it. The y prime times all the stuff without the y prime. So y prime times 2x cubed y plus cosine of x plus y minus 5y to the fourth. Still equal to the same thing over there. 4x cubed minus cosine of x plus y. Finally, we divide both sides by all of this to get y prime on the left equal to...
Wouldn't it also be divided by 2x cubed y? Oh, wait, no. Oh, wait, never mind.
Good.
Wait. Up, like the third line up, the 3x squared y squared. Is that on the other side?
Did I miss that? I might have missed it. I totally missed it. Yeah, thank you. Good call. So there should be minus 3x squared y squared there. Yeah, good eye. Thank you. So it's going to be y prime is all of that. 4x cubed minus cosine of x plus y minus 3x squared y squared divided by all of this. So the algebra is kind of gross, but the calculus is not so bad, right? Actually differentiating both sides in this first step wasn't so terrible. All of this was awful, but it's fine. So that's kind of the general idea with implicit differentiation. You are differentiating, and when you differentiate something with a y in it, well, y is really a function of x, so you always have to multiply by the derivative of y, which is y prime. The place where this comes up most of the time in this class is when you're using logarithmic differentiation. So there's kind of two distinct cases here. And one of them is more normal and one of them is less normal, in my opinion. And there was definitely a problem similar to this on the quiz. So if you haven't done the quiz yet, this is a problem that's similar to the last problem on the quiz, I believe. So let's say I wanted to find the derivative of, to differentiate. Actually, I'm going to write it this way to be at least at first more confusing. So this is probably the worst way I could write this problem. Find the derivative of, how do I want to write this? X to the secant of x. And the reason it's terrible to write it this way, I think, is because to do this problem really correctly, at least the normal way, you have to write it as y equals x to the secant of x so that you can take the natural log of both sides. So more normally, people would usually write this as find y prime for y equal to x to the secant of x. I feel like writing it this way makes it a little more obvious that you have to take the natural log of both sides. In either case, we still have to take the natural log of both sides. So when I'm sorry, I'm missing all the possible chat. Okay. So here's what I'm going to do. I'm going to take the natural log of both sides. There's also an example of this. I posted a YouTube video which had a logarithmic differentiation question. So this is an example of logarithmic differentiation. We're taking the natural log of both sides. And the reason we're taking the natural log of both sides, well, I say specifically the reason is so that we can bring down the power on the right-hand side. More generally, the reason is so that we can simplify the right-hand side. I really want to point out the derivative of this, just so you guys know, this derivative is not just secant of x times x to the secant of x minus 1. Right? We can't use the power rule here because our exponent is not just a number, right? It's got a variable in it. So when your base and your exponent both have variables, this is when you kind of have to use this logarithmic differentiation. I want to cross this out because really you don't want that at all. It's terrible. So we take the natural log of both sides, and this process is always kind of the same. Take the natural log of both sides, then bring this power down. That's why we took the natural log of that side, so we can make the right-hand side simpler to deal with. So we've got secant of x times the natural log of x. And then we're going to differentiate both sides. The left-hand side, we're going to differentiate implicitly, meaning the derivative of the natural log of some stuff. Well, I know the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Now here's a key takeaway. Whenever you're doing this logarithmic differentiation like this, and you've got the natural log of y on the left, the derivative is always going to be 1 over y times y prime. It's always going to happen. The right-hand side, we're going to always end up having to use the product rule most likely. So I've got secant x times natural log of x. The derivative is going to be, well, the derivative of secant x is secant x tangent x times we leave the natural log of x alone, plus, then we flip it, right? We leave secant x alone, and we multiply by the derivative of the natural log of x, which is 1 over x. And then there's 2 more steps, which is really just 1 more step. Here's the intermediate step that I don't think you really need to write. Multiply both sides by y. So y prime is y times all of this. You might simplify this a little bit. You might write it as, well, secant of x, tangent of x, natural log of x, plus I would rewrite this as secant of x over x. I usually skip this step though and go straight to replacing y with what y is equal to. So really my answer should be y prime is equal to y, which is x to the secant of x power, times all of this, which is going to be hard to fit in here. Secant of x, tangent of x, natural log of x, plus secant of x over x. Sorry, I know that's kind of messy there. But that's our final answer. It's the original function y times all of this here. And usually I would just skip writing, right? When I multiply both sides by y and bring that y up over here, I usually just then replace it right away with whatever y is equal to. But your answer for these should have a, right? This would not be a good final answer because your answer should be still a function of x. So we definitely need to replace that y with what we know y is actually equal to. All right, so this is most of the time how you're going to use the process of logarithmic differentiation, by just when you have a function where you have a variable in your base and your exponent. That is the typical kind of example. I think it'd be good for you guys to try one on your own. So let's go to the other side here. I want you guys to all try this one. Oh, yeah. So same process. You're going to take the natural log of both sides, bring the stuff down, and then differentiate. Why don't you guys try finding the derivative of y equal to, what is the last one? Sure, let's do something like, I don't know. I like to use the trig functions. They're kind of great. Let's do cosine of x to the x squared minus 1 power. So I want you guys to do the same sort of steps. First, take the natural log of both sides. Then bring down the power. Then finally, after you've done those 2 steps, differentiate both sides. So try that. I'll give you guys like 2 or 3 minutes. Probably 2. Also, I'm going to post that link again. So if you haven't already, oops, please go to this link to a Google form and fill out your attendance. Yeah, brackets or parentheses is fine. I like to use brackets just to kind of to show what I've got. So if you look back here, right, I use brackets because I've also got some parentheses in here. But if you use a big parenthesis there and there, that's also fine. else I wanted. Where'd you go? Good. Okay, let's go ahead and take a look at this. So again, this should be very similar to what we just did. So I have the natural log of y equal to the natural log of cosine of x to the x squared minus 1. And you can kind of even skip this step and go to the next step where you just bring down the power. So you can even say, okay, that's equal to x squared minus 1 times the natural log of cosine of x. And then we're going to differentiate both sides. So really I'm differentiating this side and I'm differentiating this side. So the derivative of natural log of y, once again, is 1 over y times y prime. The derivative of that right-hand side is, well, I'm going to have to use the product rule. So it's going to be the derivative of this, which is 2x, times, leave the other part alone, plus, then I'm going to leave this alone. And the derivative of the natural log of cosine of x is 1 over my stuff times the derivative of my stuff. Finally, so I'm going to do the last step all in one. So I'm going to multiply both sides by y. So I'm going to bring the y over. So it's going to be all of this stuff, which I like to put in brackets, but parentheses is also fine. So let's simplify all this. It's 2x natural log of x plus, well, let's actually really say it's a minus, right? Because I've got a minus there. So sine over cosine is tangent. So I'd say I have minus x squared minus 1 times tangent of x. So that's the right-hand side just simplified. And then the left-hand side, 1 over y times y prime, I'm going to multiply the y over here. But instead of writing y, I'm actually going to write what y is equal to. So I'm going to have cosine of x to the 2x minus 1. This would have been the y that we brought over, but I'm just skipping the steps so I don't have to write this again because it's kind of annoying. Are there questions about that?
Good question.
Yeah.
Isn't it supposed to be cosine of x on the first term or 2x?
Yeah, totally. Sorry, I don't know how I lost that. Good call. I will point out generally, occasionally I make mistakes. Please keep me on my toes. If you see something that looks wrong, don't hesitate to say something. Yeah, that should be natural log of cosine x. Thank you.
So when you're doing the implicit differentiation, do you always use natural log? Like you always use ln?
So here's the thing. In 16a, we did a lot of implicit differentiation problems that weren't like this, right? Where we just had a bunch of stuff with x's and y's all mixed together, like the first problem we did in class today. In 16b, we mostly use implicit differentiation just in this way, where you've got y equal to something, and then you've got the natural log of y equal to the natural log of the stuff. And so when you're taking the derivative of this, it's 1 over y times y prime. That is, I wouldn't say completely the only way we use implicit differentiation, but it's mostly the only way we use implicit differentiation in 16b.
Okay, thank you.
You're welcome. Other questions?
I have another quick question.
Sure.
So I know that you were saying that you usually use implicit when you have a variable, but how come you couldn't use this process? For example, like let's say it was like 2x raised to like the x squared minus 1, because like on the quiz that's what I was getting like confused on.
Oh, so that would also, so you say like if you had something like what, y equal to?
For example, like 2 to like the x squared minus 1, or yeah, something like that.
Like that. So here's the thing, you could totally use this process for that, but we kind of have a shortcut method of doing it this way. So actually, let's talk about that, because I think this is a really kind of important thing. If you can do it the shorter way, it's going to save you time. And is that exactly the problem from the quiz?
No, it was no.
Okay.
Yeah.
Not that I wouldn't do the problem from the quiz, but I would prefer to do one not on the quiz just so you guys can do that one on your own to kind of have the practice. So let's say we want to take the derivative of 2 to the x squared minus 1. So let me ask you guys a different question. What if my function was e to the x squared minus 1? What's the derivative of that? Or do we know that?
Is it just x squared minus 1?
Mm-hmm. The derivative is e to the x squared minus 1 times 2x. So let me ask you guys, do I need to explain this more? Because I'm happy to if I need to. Like if you want explanation about this, I'm happy to talk about it. You can even, let me ask you guys to use, so I would like to try and encourage people to use the yes, no buttons because they kind of help me see. So would you like more explanation about this? I see mostly no's. Nicole, I see a yes from you, but I'm not sure if that's because it was already on a yes before. Oh, you just changed it. Okay, so it looks like everyone is mostly okay with that. And again, I'll point out the reason why, just as a very brief explanation, is because if you're taking the derivative of e to the stuff, it's equal to e to the stuff times the derivative of stuff. Now, we could totally use logarithmic differentiation here. I can take the natural log of both sides, get the natural log of 2 to the x squared minus 1. I could bring down the x squared minus 1 like that. And then I could definitely do implicit differentiation or differentiation on both sides. The derivative of the natural log of y, as usual, is 1 over y times y prime. The right-hand side, however, I don't have to use the product rule here because I have a function, x squared minus 1, times a constant natural log of 2. So when I differentiate this, the derivative is actually much simpler. The derivative on the right-hand side is just, well, the derivative of this is 2x times the constant natural log of 2. Or if you did want to use the product rule, you could say it's 2x times natural log of 2 plus x squared minus 1 times the derivative of the natural log of 2 is 0 because natural log of 2 is a constant. So you could do it this way if you wanted to, but it's the same result. So then we end up getting y prime equal to y times 2x times natural log of 2. Replacing y with what it's equal to, we get y prime equal to 2 to the x squared minus 1 times 2x times the natural log of 2. So here's the thing. You can totally do it this way each time. And you have to do it this way, or I mean, you essentially have to do it this way, if your base is a variable and your exponent is a variable. But when your base is a constant, there's actually a more formulaic way of doing it, where we know the derivative of e to the x is e to the x, and the derivative of e to the stuff is e to the stuff times the derivative of stuff. Well, e is a constant, right? It's about 2.7. And the thing about it is this rule is true for other problems, for other constants as well, with an additional little piece. So the derivative of 2 to the x is 2 to the x times the natural log of 2. When your base is something other than e, you have to multiply by the derivative of the natural log of the base. This would also work if the base was e, because if it was e to the x, the derivative is e to the x times the natural log of e, but that's just 1, so we don't write it there. And then there's a similar formula for the derivative of 2 to the stuff. Derivative of 2 to the stuff is 2 to the stuff times the derivative of the stuff times the natural log of 2, which is exactly what we got here, right? The derivative of 2 to the stuff was 2 to the stuff, so there's the stuff, times the derivative of that stuff times the natural log of 2. more generally, writing green here, if your base is something other than e, the derivative of a to the x is a to the x times the natural log of a. And the derivative of, I'm going to write it more like the book would write it here. The derivative of, say, a to the, I'm still going to say stuff. The derivative of a to the stuff is a to the stuff times the derivative of the stuff times the natural log of a. So a very long answer to your question. For this kind of question, you could totally do it this way, using the natural log of both sides, but you could also do it this shorter way, where you say, oh, I know the derivative if it's a constant base to some exponent. The derivative is that exact same thing, right? You always get what you started with for exponential functions, times the derivative of the exponent times the natural log of the base. So that'll always work. But it doesn't work for problems like the previous one, right? This one, we have to do it this longer way where we take the natural log of both sides. This other one, you can do it that way, but you don't have to. You can also do it this way. I'm going to go turn down the heat real quick. It's getting super hot in this room. I'm sure I mentioned that my wife and I are unfortunately in the wrong offices for ourselves. I'm in the room that's really hot. She's in the room that's really cold, and I like to be cold and she likes to be hot. So what are you gonna do? Okay. There was somewhere else I wanted to, oh, I know. There was one other thing I wanted to mention about this logarithmic differentiation, but I don't want to say too much about it if it doesn't apply to anyone, which it certainly might not. So I'm gonna do one real quick example. And we'll see if I actually finish it. So sometimes people like to use logarithmic differentiation even when it's not absolutely necessary. For example, I want to find the derivative of y equal to, let's make it not too terrible, x squared plus 1 to the 4th over x to the 6th times sine square root of x. Well, I should say there's no good reason. Has anyone talked about in their class doing a problem like this using logarithmic differentiation? Any yeses? Sorry, the problem is my thing doesn't get big enough, so I can't see all you guys, which is too bad. I guess I could maximize this. That would be smart. Even then, though, I don't think.
I think Fam has tried, but I don't think like it made sense. I think though.
Yeah. So the idea there. So let me just show you real quick. I don't think so. Personally, I would still just use probably the quotient rule and the product rule and the chain rule. But you can totally do this. You can say the natural log of y equals the natural log of all this stuff. And then you can break this apart using the rules of logarithms. So here's how this is going to break apart. It's going to be the natural log of x squared plus 1 to the 4th minus the natural log of x to the 6th minus the natural log of sine squared of x. I kind of did 2 steps in one there. It's really the natural log of the top minus the natural log of the bottom, but then the natural log of the bottom is a product, so it's the natural log of this plus that, but the minus sign distributes. The way I always remember it is that all the top stuff ends up with a positive natural log, all the bottom factors end up with a negative natural log. And then I bring the powers down. So the natural log of y equals 4 times the natural log of x squared plus 1 minus 6 times the natural log of x minus, this is sine of x quantity squared, so that's 2 times the natural log of sine of x. And then we can differentiate both sides more easily. We totally could have differentiated this straight away using the chain rule, quotient rule, and product rule. But here now it gets a little bit simpler. So I get 1 over y times y prime equal to 4 times the derivative of this, which is 1 over my stuff times the derivative of my stuff, minus 6 times the derivative of this, which is just 1 over x, minus 2 times the derivative of the natural log of some stuff, which is 1 over the stuff times the derivative of the stuff. Finally, I'm going to do two things at once. I'm going to multiply both sides by y, but replace y with what it's actually equal to. So I'm going to get y prime equal to y, which is x squared plus 1 to the 4th, over x to the 6th times sine squared of x, times all of this stuff here, which I'm going to simplify just a little bit. 4 times 2x gives me 8x over x squared plus 1. 6 times 1 over x, I would just say is 6 over x, or minus 6 over x. And minus 2 times cosine over sine is minus 2 times cotangent of x. So sometimes people, when they have a really complicated quotient with a lot of different factors, sometimes people will do this logarithmic differentiation. It is not absolutely necessary, but it is kind of useful. A more typical question, so here's kind of the last question we'll ask like this. A more standard question that I would expect to see on an exam, if I was giving an exam in this class, would be something where you actually did the natural log of that to start off with. So instead of finding the derivative of y equal to just some quotient, and I also asked a question like this on the quiz, I believe. What time is it? Oh, yeah, we got time. I would want to find the derivative of something like y equal to the natural log of something like that. So something like x cubed times, let's do, sure, times cosecant of x over the square root of x squared plus 1 times, let's just do that. So here, there's no need to take the natural log of both sides because you've already got a natural log on the right. The idea here is that you're just supposed to simplify this, right? So you should not take the derivative straight away. I don't want to say that the derivative is 1 over all of this times the derivative of all of this, because that's going to be kind of gross. Before I differentiate, I'm going to simplify. I'm going to say, oh, well, this is the natural log of x cubed plus the natural log of cosecant of x minus the natural log of x squared plus 1 to the 1/2. I do recommend rewriting any roots as powers. And also, so some people differentiate here. I think you should simplify one more step. I think you should bring all of the powers that are powers of the whole thing down. So I'm going to write this as 3 natural log of x plus the natural log of cosecant of x minus 1/2 times the natural log of x squared plus 1. I would like to emphasize here, you cannot break this natural log up any further. When you got the natural log of something plus something else or something minus something else, you're stuck with that. And so if we're stuck with that, we can't bring down this power either, because it has to be a power on the entire kind of argument tail to bring it down in front of the natural log. But now we've simplified as much as possible, we can differentiate. So y prime is going to equal 3 times 1 over x. The derivative of the natural log of cosecant is 1 over cosecant of x times the derivative of cosecant of x is negative cosecant of x times cotangent of x minus 1/2 times the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times 2x. And although you don't, I wouldn't simplify it really, I would leave it like this, but here there's a couple nice things you can simplify. So we can write this as 3 over x. Here, a cosecant can cancel, and you get just minus cotangent of x. And here, a 2 can cancel, and you get minus x over x squared plus 1. So that does simplify a bit. Okay. All right, I think that's enough about these logarithmic things. Again, I would encourage you to make sure you're comfortable with the derivative of e. There's one more thing I should probably say. Which is kind of related, but not super related. So just like
James, sorry, I had a question about the last problem.
Sure.
Did you by any chance forget to add, you know how you took the derivative of y, and then you'd have to multiply y on both sides?
So the difference between I just erased it. So the difference here is that here I didn't take the natural log of both sides. I was just starting with y equal to the natural log of something. So when I differentiated the left side, I just got y prime. Whereas in the previous problem, I started with something like this, y equals to some function of x, right? Like x cubed times sine of x. And although you could totally just use the product rule here, we did something like this, but I'm gonna take the natural log of both sides. And then I'm gonna simplify. And we're gonna 3m as well. So then if I differentiate this here, the derivative of natural log of y is 1 over y times y prime. The derivative of 3 times natural log of x is this. The derivative of natural log of sine x is this. So the difference here is that in this problem, I took the natural log of both sides. So when I differentiated this, I did get a 1 over y times y prime. Whereas in the other problem, I did not take the natural log of both sides.
Oh, okay, I see. Thank you.
You're welcome. Good question. The other thing I wanted to mention was that just like when, so I know before I was saying like the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And when you have a different base, it's essentially the same formula. It's a to the stuff times the derivative of the stuff. The only difference is you also have to multiply with the natural log of your different base, right? This is the part that kind of separates it. Well, there's a similar thing that's true if you're doing derivatives of logarithms with different bases. So we've seen a few times here that the derivative of the natural log of x is 1 over x. And that the derivative of the natural log of some stuff is 1 over the stuff. It's kind of really squeaky. Times the derivative of the stuff. And there's a very similar formula if your base is something else. So if I'm taking the derivative of, say, the log base a of x, the derivative is 1 over x. But you also have division by the natural log of a. So the way I kind of think of it is when it's an exponential function where your base is something else, like a, you multiply by the natural log of a. When it's a logarithmic function where your base is a, you divide by the natural log of a. And that's also true for the chain rule version. If we take the derivative of log base a of some stuff, it's, and I kind of write it out this long way, it's 1 over the stuff times the derivative of the stuff, just like it would be for the derivative of the natural log of some stuff, but then we also have to divide by the natural log of a. Or I write it as times 1 over the natural log of a, it's more convenient that way, but that's essentially what's happening there. So for example, if I said, sorry if you guys can't see that very well, if I said I wanted to find the derivative of log base 3 of, what do I want to do here? Something not too terrible. X to the 4th plus cotangent of x, the derivative would be 1 over the stuff times the derivative of the stuff, which is 4x cubed. The derivative of cotangent is minus cosecant squared of x. And then we also need a 1 over natural log of 3. Now this looks kind of unwieldy. A lot of people would probably simplify this. I would leave it as is, but if you feel like you need to simplify it, you can simplify it as one fraction. This is on top, 4x cubed minus cosecant squared of x. And this times this is on the bottom. So x to the 4th plus cotangent of x times a natural log of 3. So let's move on and talk about exponential growth and decay just a little bit. I always kind of think it's funny, I don't know, funny, but exponential growth and decay, I mean, yes, they're calculus topics, but it doesn't feel like we're doing a whole lot of calculus with them. So exponential growth / decay. Here's kind of the real idea, actually. Exponential growth and decay come from the fact that, specifically, I like to think about growth. If you're saying something is growing exponentially, well, where that's coming from is you're saying that, so let's say y is, y, or y of t, is the population at time t. And where this exponential growth equation comes from that we haven't written down yet is by saying that dy dt, the rate of change of the population with respect to time, so how fast the population is growing, is proportional to the population size. So when I see this equation, what I actually think of is I'm saying, oh, all this means is that how fast the population is growing depends on how many people there are, right? If there's more people are going to make more people faster. So the more population you have, the faster the population grows. Another way of saying this is that the relative population growth rate is constant. That's kind of not super important. But what ends up happening, and as soon as we start talking a little bit more about antiderivatives and there's another thing, differential equations, we might come back and revisit this, how to solve this exactly. But what I'm going to say here is that the solution to this is y equal to c e to the kt, which I imagine many of you have probably seen, especially if you've ever taken chemistry. But even if you haven't. How is that a solution? Well, let's take a look. If I take the derivative here, y prime, or dy dt, either way you want to write it, I have a constant times e to a constant times t. The constant hangs out, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative of k times t? Just k, right? It's like saying that the derivative of 7x is just 7. The derivative of k times my variable is just k. But now, take a look. This is my y. So the derivative dy dt here is equal to y times k, or k times y. So all I want to point out at this moment is that, oh yeah, when you're solving this differential equation, where the rate of growth, the derivative is proportional to the population size, the solution to this differential equation is the exponential growth or the exponential decay model. Okay, now as far as answering exponential growth decay questions, knowing this isn't super important, but when we get back to differential equations, it becomes a little important. So let's look at an example or two. Also, I know what I want to say. So just in case not everybody has seen it yet, once again, there's the link to the Google form attendance sheet. If you could all please make sure you go there and enter your student ID number as well as what class it's for, I would appreciate it. And we're going to do that every class, so just get used to doing that at the beginning of class for future classes. You could probably even just bookmark the link for yourself if you want to, so you don't have to wait for me to post it up in general. But let's say we have this sort of problem. This is definitely kind of going to be a wordy problem. So I'm going to try not to write out too much here. Let's say we have a bacterial culture. Initially has let's say something like 250 cells. And 3 hours later, there are 600 cells. Usually the first thing, we don't even ask, but often is find a model for the population growth. Meaning, so we want to find a model. The model is y equals c e to the k t. The question here really is, when they say find a model, they mean find the constants c and k for this particular situation. Because really the question we want to answer, so here are the questions we actually want to answer. We want to answer something like, how many cells will there be after, I don't know, 10 hours from the initial observation? Or how long until the number of cells is 1,000? Those are the kinds of questions we actually want to answer. But before we can answer either of them, we have to figure out what the constants c and k are. And typically, not always, but typically c is really easy to know. If you know how much stuff there is at the initial time, or at time equal to 0, or t naught, that's what c is. We could also actually plug things in, right? Oh yeah, I like making this little chart. So when time is 0, I have 250 cells. And when time is 3 hours, I have 600 cells. So that makes it easy for me to make sure I plug the right thing in for t and for y. So plugging in 0 for t and 250 for y, I get 250 equals c times e to the k times 0. But k times 0 is 0. And what's e to the 0?
One.
Thank you. Yes. I really do want you guys to talk. I like hearing voices. Also, my voice is getting better because I'm not talking too much, but the more you guys talk, the more rest you give my voice. So e to the 0 is 1, so I get 250 is just equal to c. So usually that constant c there is just your initial value, how much stuff you have at time 0. So then we can say y equals 250 e to the k times t. And then we can use the other piece of information, time equals 3 and y equals 600, to solve for k. So we've got y equals 600 and t equals 3. And solving this, solving for k here, or solving for anything within the exponent, is almost always the same few steps. First, we need to isolate the e to the whatever, so we divide both sides by this coefficient. So 600 divided by 250 equals e to the, usually people rewrite this as 3 times k, just because it feels more normal to write the number before the letter. And then, I'm going to give myself a little more room here. Then we take the natural log of both sides, because we want to take the natural log of e to the stuff to get rid of the natural log of the e and just get the stuff. Also, I'm going to simplify this a little bit. That definitely reduces to 60 over 25, which can probably reduce even further. That's equal to the natural log of e to the 3k. But the natural log of e to the 3k is just 3k. And when you take the natural log of e to the stuff, you just get the stuff. So I'm running out of room here. Let's go to the other side. So I'll remind you, I had the natural log of 60 over 25 equal to 3k. And then finally simplifying that, divide both sides by 3, k equals, this simplifies to the natural log of, let's see, I can cancel a 5 for both of those. 60 divided by 5 is 12. 25 divided by 5 is 5. And then I could write divided by 3. I'd rather write times 1/3. It just looks a little bit nicer, but either way is fine. Okay, so my model y equals c e to the kt is really y equals 250 e to the k, which is 1/3 natural log of 12/5 times t. Sometimes people put brackets around all that so that you realize that that's all the exponent. There are other ways of writing this. Some people prefer to make their base not e. That is not what I prefer to do. But there are other versions you might see this. Like you might see someone else write this as like, you could see someone write this as y equal to 250 times 12/5 to the t over 3. That would also be a way of writing this. I don't want you to select that though. I think this is the way you should write it. If this concerns you, we can talk about it later. So then we had two questions. Question one was, how many cells will there be after, I think I said 10 hours? Yeah. This is definitely the easier type of question to answer because you're just going to set t equal to 10. So the answer here, if t equals 10, I'm going to get y equal to 250 e to the 1/3 times the natural log of 12/5 times 10. And I would just leave my answer like that if I didn't have a calculator. Or even if I did have a calculator, right? This is the exact answer. You can then pull out a calculator if you really want to and say, okay, so I'm going to do this part here. I'm going to do 10 divided by 3 times the natural log of 12/5. And let's see, natural log of 12 divided by 5. And then I'm going to do e to that. So let's see, where's my e to the button here? It's somewhere. E to the second answer. It's about 18.5, and then I'll multiply that by 250. So I get about 4,627. Which seems maybe reasonable, I don't know. Let's see. It took 3 hours to more than double. So another 3 hours, it would more than double to something more than 1,200. Another 3 hours, it would more. Yeah, that seems in the realm of reasonable. It's always good to think about if your answers make any sort of sense. The other question was, when will we have 1,000 cells? And to answer that question, we set y equal to 1,000 and solve t. So typically, with these exponential growth and decay problems, after you've found the model, you're either given a time and asked to figure out how much stuff you have, or you're given an amount of stuff and you have to figure out what time is it when we have that amount of stuff. But usually it's they give you one thing and you find another thing. So that's kind of it. So I'm going to set y equal to 1,000. And solving for t is going to be very much like solving for k when we were doing the solving for k part. I'm going to set 1,000 equal to all of this, except I have a t instead of a 10. 250 e to the 1/3 natural log of 12/5 times t. And I'm going to solve for t. I'm going to do it very much like I did it for k. First, I'm going to divide both sides by 250. And 1,000 divided by 250 is just 4. So I get 4 equal to e to the all that, e to the 1/3 natural log of 12/5 times t. And then whenever I'm trying to solve for something in the exponent here, I'm going to take the natural log of both sides. So I'm going to try and squeeze it in. I'm right over here. So the natural log of 4 equals the So here's the thing. I'm trying not to do too much writing. The natural log of e to some exponent is just the exponent. So when I take the natural log of e to all of this stuff here, I'm just going to end up getting all that stuff in the parentheses. So right, so the natural log of 4 equals to the natural log of e to the all of that, which I'm not going to rewrite, gives us the natural log of 4 equals just what's in the parentheses here. The 1/3 times the natural log of 12/5 times t. And then solving for t, well, I'm going to multiply both sides by 3. So you get 3 times natural log of 4. And divide both sides by natural log of 12/5. And that's my t value. And then again, I would leave it like that. If I want to get a decimal approximation, I pull out my calculator and I do 3 times the natural log of 4 divided by the natural log of 12/5. And I end up with 4.75. So about approximately. So t is approximately 4.75 hours, or 4 hours and 45 minutes. Okay. So we can definitely do more examples like this in the future, but since we have a limited amount of time, I would like to do at least a couple antiderivative things. So here's what I'll say first. A lot of this class focuses or is centered around antidifferentiation. So we're going to talk about the methods of antidifferentiating, but before we get to all that, we have first to think about kind of the idea of antidifferentiation. And the whole idea is that an antiderivative exactly undoes what a derivative does. Also, we often use capital function letters to represent antiderivatives. So for example, if I said my function f of x was 4x cubed, then I could say that an antiderivative, which is capital F of x. So if you see people using these letters without any sort of explanation, they typically mean that this capital F is the antiderivative of this little f, and this little f is the derivative of this capital F. That is usually a safe assumption to make if no one has said anything about what they're doing. So the antiderivative of 4x cubed is x to the 4th. Right, the derivative of x to the 4th is definitely 4x cubed. So the antiderivative of 4x cubed is x to the 4th. Now, x to the 4th is one answer. So is x to the 4th plus 7. Right, because this function and this function, they both have the same derivative. And so does this function. So really what we end up doing when we find an antiderivative is we say, well, it could actually be any function that looks like x to the 4th for this particular example, plus any constant you want. So when you find an antiderivative of a function, you're actually finding a family of functions, right? There's technically an infinite number of answers here, x to the 4th plus any real number you want. Now, we say there's still just one antiderivative because there's only one type of antiderivative, but it is important to realize that there's actually technically a lot of different answers to this question. They all are essentially the same, but they are technically different. So just to make sure we are familiar with this, so when you go from 4x cubed to x to the 4th, you're doing the antiderivative. And when you're going from x to the 4th to 4x cubed, you're doing the derivative. And they undo each other. I kind of like to think of it, although not exactly. To me, it's kind of like how inverse functions undo each other. For example, if f of x is, I'm going to make up an easy one, like x cubed plus 2, then the inverse function g of x is x minus 2 to the 1/3 power. All I did was undo the steps in the opposite order, right? Here I cubed and then added 2. Here I first subtracted 2 and then cube rooted. These functions undo each other, right? F of 2, now let's not use 2. F of 3 is equal to 3 cubed, which is 27, plus 2, which is 29. G exactly undoes that. G of 29 equals 29 minus 2 to the 1/3 power, which is the cube root of 27, which is 3. So F did something to 3, and I got 29, and then G undid that and got me back to 3. In the same sort of way, differentiating and antidifferentiating undo and redo what you're doing to the function. So what I'm trying to say with that is, I'm gonna erase this. Let's say my function, f of x, let's do something slightly different. Let's say my function is x to the 5th. The antiderivative, well, so here's what we're going to see for antiderivatives. When it's a power of x, the derivative of a power of x, using the power rule, the power is 1 less, right? I know that the derivative of x to the nth power is n times x to the n minus 1 power, right? The derivative of x to the 5th would be 5x to the 4th, so on. The antiderivative does the opposite stuff, meaning instead of bringing down the power or multiplying the power and then subtracting from the power, we do the opposite things in the opposite order. So first I'm going to add 1 to the power. In fact, I could even write 5 plus 1. And then I divide by the new power. And then I throw on a constant at the end there. So here, that's x to the 6th over 6 plus c. So there I did the antiderivative. So I anti-differentiated. But then if I re-differentiate, if I take the derivative, so if I find the derivative, if I differentiate, well, f prime of x, that's the derivative of x to the 6th over 6 plus c. I would rather actually write this to make it a little bit easier. I don't want to think about even having to use the quotient rule. You don't have to use the quotient rule if you're dividing by a constant. But it might be easier to visualize if you think of it as 1/6 times x to the 6th plus c. Then the derivative, this 1/6 is a constant that just hangs out. And what's the derivative of x to the 6th?
6x to the 5th.
Thank you. Oh, except the derivative of c isn't c. What's the derivative of c? Somebody else?
0.
Yeah, thanks. That might have been the same person. It's all right. But look, these 6's cancel, and you just get x to the 5th, which is the function you started with. So I really want to make it 100% crystal clear to everybody. Anti-differentiation and differentiation undo each other. If you do one and you do the other, you get back to where you started. It's really important to make sure you understand that. So what this ends up leading us to is kind of the fact that any functions you know how to differentiate, you know how to anti-differentiate those results. Meaning, and I'm sure there's a list in your textbook somewhere. That reminds me. It's a different thing. Come on. So I know that, well, actually, so apologies. For any function that looks like x to the n, the antiderivative is x to the n plus 1 divided by n plus 1 plus c. Because the derivative of this is equal to that, right? If I took the derivative, and again, I would really rather write this as 1 over n plus 1 times x to the n plus 1. Right, the derivative of this is equal to, well, again, this constant just sticks around in front. The derivative of x to a power, I'm just going to use the power rule. You get n plus 1 times x to the n plus 1 minus 1. And then the derivative of c is just 0. So 1 over n plus 1 times n plus 1, those cancel, I just get 1. X to the n plus 1 minus 1 is just x to the n. So the derivative of this is equal to that. And so I want to make this, again, I'm going to say this a lot. I want to make this clear, right? If I say the derivative of this function, x to the n plus 1 over n plus 1, is equal to x to the n, then it also means that the other direction is true. the antiderivative of this function, x to the n, is equal to x to the n plus 1 over n plus 1. And there's one small extra thing I should say here. This is true as long as n is not equal to -1, right? If n was -1, we'd be dividing by 0 here, and that'd be a problem. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. Or as I think of it, when we antidifferentiate the power of x, we add 1 to the power and then divide by the new power. So for example, if g of x is equal to x to the 13th power, then the antiderivative, which I'm going to write for now as capital G of x, is x to the 14th divided by 14 plus c. Or if h of x was equal to 1 over x to the 9th power, I'm not going to try and use some wacky anti-quotient rule, which doesn't exist. There really isn't an antiderivative quotient rule. Instead, I'm going to rewrite this. I'm going to say, oh wait, I can really rewrite that as h of x equal to x to the -9th power. And then the antiderivative of that, again, I'm just going to use the same rule. I'm going to take my expression and add 1 to the power and divide by that new power. So here I'm going to end up with x to the -8 divided by -8 plus c. And I don't really like having a negative in my denominator like that, so I would probably write this as -1/8 times x to the -8 plus c.
So how do we know what c to use? Like,
so c should just be a blanket statement c. Like c is representing any possible constant. Sometimes if you're given what's called an initial value problem, which we're not to yet, I don't think, sometimes you'll have to solve for c, but for now, you're just going to write c and think it could be any constant. You shouldn't be writing a specific value for c yet. That seem okay?
Yeah. Do you think you could do like oh, never mind, we're out of time.
Go ahead. No, we're not kind of out of time. Well, we are, but.
Do you think you could do like another example?
Definitely. So what I wanted to say was that, and also if you have to go, I totally understand. Class is technically over, so feel free to leave if you need to. But here's just 1 or 2 more examples. So here are some other functions we know. I know the derivative of sine of x is equal to cosine of x. So I can say if my function is cosine of x, then the antiderivative is sine of x plus c. So anything you know the derivative of, you know the antiderivative of that derivative is just the function you started with. Here's another example. If g of x is equal to tangent of x, then the antiderivative, capital G of x, oh, sorry. Let me back that up completely. What's the derivative of tangent of x? Secant squared of x. So since I know the derivative of tangent is secant squared, I know that the antiderivative of secant squared is tangent of x plus a constant. So that's kind of the idea. Anything you know the derivative of, you know the antiderivative of that result. Specifically, if f of x equals e to the x is the derivative of e to the x, the antiderivative is e to the x plus c. So e to the x is the only function that is its own derivative. It's also its own antiderivative. It's kind of cool. And then one last one, and we'll leave it there, and we'll talk more about this for sure on Thursday. What's the derivative of the natural log of x? Somebody.
1 over x.
Right? So since I know the derivative of natural log of x is 1 over x, I know that the antiderivative of 1 over x is the natural log of x plus c. That's actually technically not exactly correct. There's actually an absolute value in there, but we'll clarify that next time. So this is what I really want to make absolutely clear. things, right? I know the derivative of sine is cosine. I know the derivative of tangent is secant squared. I know the derivative of e to the x is e to the x. I know the derivative of natural log of x is 1 over x. So I know that the antiderivative of each of these things is each of those things. The antiderivative of cosine is sine because the derivative of sine is cosine. The antiderivative of secant squared is tangent because the derivative of tangent is secant squared. The antiderivative of e to the x is e to the x because the derivative of e to the x is e to the x. And the antiderivative of 1 over x is essentially natural log of x because the derivative of natural log of x is 1 over x. That's really, really, really the relationship that's important that you understand. All right, we should end it there because I do have another class to teach in a little bit. So I will see you all on Thursday. For those of you, again, please do submit the quiz sometime today. Sorry about the email confusion. Make sure you fill out your attendance. And if you have questions, start a discussion thread on Canvas. I'm happy to make videos for you guys if there are things you want to see. You can also email me, but the discussion thread is better because then everyone can see it and add to it. So if you want to see things, let me know. I will make it happen. I'll see you all on Thursday. Bye.
Thank you.
You're welcome. Bye.